All right, let's talk batteries. Ever really wonder how they work? I mean, what's happening on a chemical level? Well, today, we're going to tear one down, metaphorically speaking. We're going to deconstruct a classic galvanic cell problem step by step to really see how it makes electricity. Let's dive right in.
Okay, so here's our setup. Looks a little complicated, right? On one side, you've got a platinum electrode with chlorine gas bubbling around it. On the other, a solid gold electrode sitting in a solution of gold ions. Right now, they're just two separate beakers, but once we connect them, they become a power source. The real question is, how? Stick with me and you'll get it.
So, where do we even start with something like this? You start with the most basic question of all. In this chemical dance, who's leading and who's following? Who's giving up electrons and who's grabbing them? If we can figure that out, everything else will fall into place.
To find our answer, we look at these numbers called standard reduction potentials. You can think of it as a score for how badly each chemical wants to grab electrons. The higher the score, the bigger the appetite. So, by comparing the potentials for gold and chlorine, we can pinpoint which side is the anode, where electrons are lost, and which is the cathode, where they're gained.
And here it is, the one simple rule you need to remember. The reaction with the higher potential is the one that wins the electron tug-of-war. It gets reduced. It's really that simple. Gold clocks in at 1.50 volts, which is higher than chlorine's 1.36. So that tells us the gold electrode is our cathode, and the chlorine side has to be our anode.
Okay, so now we know what's happening on each side. To see the whole picture, we need to combine them. But you can't just smash them together. Chemistry is all about balance. The number of electrons released at the anode has to be exactly the same as the number of electrons accepted at the cathode. So we'll do a little multiplication to find a common number of electrons, which in this case is 6.
And boom, here's our final balanced equation. This tells the complete story. For every 2 gold ions that turn into solid gold, 6 chloride ions have to become chlorine gas. It's this perfect, balanced exchange of 6 electrons that creates the steady flow of current through the wire.
So what kind of power are we getting out of this thing? To find the voltage, or the standard cell potential, all you do is subtract the anode's potential from the cathode's. We get 0.14 volts. Now the number itself isn't the most important part. What's crucial is that it's positive. A positive voltage means the reaction will happen all by itself. It's spontaneous. It's a green light.
All right, enough with the theory. We've figured out what should happen. Now let's see what happens in the real world when we actually connect the circuit and let this thing run for a while.
This is where the chemistry gets real, where you can actually see or measure a change. We let a current of 0.5 amp flow for 30 seconds. What physically happens to our electrodes? Does one get heavier? Lighter? Let's find out. We can figure this out with a really clear 4-step roadmap. First, we'll calculate the total amount of charge that moved through the wire. Then, we use a special number called Faraday's constant to convert that charge into a number of moles of electrons. From there, our balanced equation tells us how many moles of gold that corresponds to, and finally, we convert that to grams. And the answer is, the gold cathode gets heavier, specifically by 0.01 grams. That's because those gold ions in the solution are literally plating themselves onto the electrode as solid gold. But what about the platinum anode? Well, its mass doesn't change one bit. It's just there to provide a surface for the reaction to happen. It's not actually part of the reaction.
Okay, now for the really fun part. Everything we've done so far assumes these perfect, standard 1 molar concentrations. But what happens when we start messing with those concentrations, just like the students in this problem did? This is where electrochemistry gets really powerful.
So one student has an idea. They take out the standard gold solution and replace it with one that has some unknown concentration. They fire up the cell and they measure the new voltage. It's dropped a bit, from 0.14 volts to 0.12 volts. The question is, can we work backwards from that new voltage to figure out the exact concentration of that mystery solution?
You bet we can. And the tool that lets us do it is called the Nernst equation. This equation is like a magic translator. It connects the perfect standard conditions voltage that you'd find in a textbook to the actual real-world voltage you just measured. It does this by factoring in the concentrations of your reactants and products. So all we have to do is plug in the numbers we know. Our new measured voltage of 0.12, the standard voltage of 0.14, and the fact that 6 electrons are being transferred. We do a little bit of algebra to solve for that one unknown piece, and there's our answer. The mystery concentration is 0.097 molar. Pretty cool, right?
Now, a second student comes along with an even more clever idea.
They say, forget the chlorine side altogether. What if we build a cell using 2 gold electrodes, but we put them in 2 different concentrations of gold solution, the standard 1 molar one and the 0.097 molar one we just discovered?
This kind of setup is called a concentration cell, and it works because nature always wants to find balance. The universe doesn't like having one side more concentrated than the other, so a reaction will start spontaneously to even things out. The dilute side becomes the anode to create more gold ions, and the concentrated side becomes the cathode to use them up.
So what's the voltage here? Well, the standard potential is 0 because the electrodes are identical. The entire voltage is generated purely by that difference in concentration. We can use the Nernst equation one last time to calculate it, and it tells us this cell will produce a small but definitely measurable voltage of 0.02 volts.
Okay, we've been through a lot. We've solved every part of this puzzle. So let's just zoom out for a second and quickly recap the key electrochemical tools we use to get from that initial diagram to a full understanding of 2 different types of cells.
We really covered the big ones. We saw how to look at a table of potentials to figure out our anode and cathode. We calculated the standard voltage of the cell. Then we used Faraday's laws to connect the electrical world of current and time to the physical world of mass. And finally, we used the powerful Nernst equation to see what happens when we leave the perfect world of standard conditions.
And this is why this stuff matters so much. This isn't just some abstract problem from a textbook. These exact principles, reduction, oxidation, potential, concentration, are what make every battery work. The one in your phone, in your laptop, in an electric car, they all run on this fundamental science.
And that's our deep dive. The biggest takeaway here is seeing how these individual concepts all stack together, letting us analyze a complex system from the ground up. But I'll leave you with one last question to chew on. We've focused a lot on concentration, but what else could change a cell's voltage? What about temperature or pressure? That's your next puzzle to solve. Thanks for joining me.